Okay, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have started looking into the modeling of simple system, 3-bus system, and essentially this was the system we have considered, bus 1, bus 2 and bus 3, and so far we have not considered any transformer in this system. And then we have written down the detailed equation, and after writing down the detailed equation we have obtained the following structure. So, where I1 IABC, I2 IBC, I3 IBC are the three current vectors. For example, let us again recap where I1 IABC be essentially I1A, I1B, I1C transpose. So, this is basically a 3 cross 1 vector. Similarly, let us say II, it is better to write II. I is of course is equal to 1, 2, 3 here. Similarly, VI ABC is also a vector VIA, VIB, VIC transpose. So, this is also a 3 cross 1 vector. So, that means this is basically a 9 cross 1 vector. And this is also a 9 cross 1 vector. And so then therefore, and this would be a 9 cross 9 matrix where each of this block, that is this one, this one, this one, each of this cell would be 3 cross 3. So, now here, now of course 9 is equal to 3 into 3. So, 9 is equal to 3 into 3, that means 3n, where n is the number of buses. And here again we can see that the entries, what are the entries? For example, this entry corresponding to I1 ABC and corresponding to V1 ABC, that is nothing but the sum total of the 3 cross 3 admittance connected at bus 1. Similarly, for bus 2, this particular block diagonal element is nothing but the sum total of the admittances connected at bus 2. For example, at bus 2 there are actually 4 3 cross 3 admittances connected, this one, this one as well as this one, and then and of course at bus 3 also the corresponding self block matrix, block 3 cross 3 matrix is nothing but the sum total of the admittances directly connected to bus 3. What about the off diagonal 3 cross 3 block matrices? Of course, those 3 cross 3 block matrices are 0 whenever there is no direct connection between any two bus. For example, here in this example, between bus 1 and bus 3 there is no direct connection. So, as a result, the block 3 cross 3 matrix, that is basically the entry 1 3 and the entry 3 1, these are all null matrix. Please note that these are nothing but 3 cross 3 null matrix. These are nothing but 3 cross 3 null matrix. So this is also 3 cross 3 null matrix. So then therefore whenever there is no direct connection between any two buses, the corresponding off diagonal block 3 cross 3 matrix would be a null matrix. And whenever there would be a direct connection between any two buses, for example between bus 1 and 2, the corresponding off diagonal block 3 cross 3 matrix is nothing but the negative of the admittance connected between bus 1 and bus 2. As an example, between bus 1 and 2, the admittance connected is Y2 AC ABC, and here in this matrix, this particular element is minus Y12 ABC, right? And then of course similarly for this element 2 1 is also the same, and for the element 2 3 as well as for the element 3 2. So this principle holds good for any general system. So then therefore for an n bus system, so I call that this is the I injected vector. So this vector is called I injected vector. So therefore for an n bus 3 phase unbalanced network, the equation is again I is equal to YV. So this big matrix I am calling I, sorry, this vector is being called as I, this vector is called as V, and this matrix is called as Y, right? So I is equal to YV, where I would be a 3n cross 1 vector, V would be a 3n cross 1 vector, and Y would be a 3n cross 3n matrix. Correct? And I would be essentially, and what about the elements of I? So elements of I would be say I1 ABC transpose, I2 ABC transpose, dot dot dot, In minus 1 ABC transpose, In ABC transpose, whole of transpose. V is again V1 ABC transpose, V2 ABC transpose, dot dot dot, Vn minus 1 ABC transpose, Vn ABC transpose, whole of transpose, right, where I ABC is is actually, as I said, IIA, IIB, IIC transpose and VIABC is. So basically this is a column vector. So from this column vector we have made it a row vector. So then therefore everything is a row vector, and then because it is a row vector, so after that to make I as a column vector we have taken the final T. So then therefore individual transpose is to make the corresponding column vector to a row vector, and then we have taken an overall transpose to make the overall row vector to an corresponding column vector. Same is also true for this vector V, and VIABC is, as I said, VIA, VIB, VIC. So this is T. And the elements of Y is that the self, or rather diagonal, block diagonal 3 cross 3 matrices are, I should write for Y matrix. So this Y matrix is nothing but the so called bus admittance matrix. So for this Y matrix, block diagonal 3 cross 3 block diagonal 3 cross 3 element is that is equal to the sum total of all 3 cross 3 admittance matrix sum total of all 3 cross 3 admittance matrices directly connected to bus I. So this is, we should write that block diagonal 3, so block diagonal 3 cross 3, I should say that it is ith element. So it is a 3 cross 3, but it is an ith element. Okay. So and then block diagonal, and then block diagonal, block of diagonal element, that is actually there are two cases. One is negative of the 3 cross 3 admittance matrix directly connected between bus I and bus J. So this is block of diagonal ijth element. We can say that this is ijth element, ijth element, okay, where I is not equal to j. where I is not equal to j, you should also write that I is not equal to j, because when I is equal to j, that possibility we have already taken care of in the block diagonal 3 cross 3 ith element. So, block of diagonal ijth element where I is not equal to j, that is equal to negative of the 3 cross 3 admittance matrix directly connected between bus I and bus j in the network, bus j in the network, in the network, and it would be 0 if there is no direct connection between bus I and bus j. So, obviously, if there is no direct connection, so this 0 is nothing but, again we repeat, this is nothing but 3 cross 3 null matrix. So, that is how for an n bus system we would be able to form the Ybus matrix. Now, here, so I mean this is essentially the nutshell that how to model a 3-phase AC system, unbalanced AC system in the absence of any transformer. Now, let us see that how the presence of the transformer can be taken into account. So, presence of transformer. So, to do that, let us take a simple system, let us say bus 1, bus 2, between bus and then bus say 3 and then bus 4, and between bus 2 and 3 there is a transformer, right. So, just a very simple system. Earlier we have considered a 3 bus system, but now we are simply considering a 4 bus system. So, let us see that how this 4 bus system where a transformer is connected can be incorporated. Now, again bus 1 is basically that can be modeled as, say this is bus 1. So, I can say that this is a 3 cross 3 matrix. So, I say that this is a, so the model of this system would be bus 1, bus 2, bus 3, bus 4. Between bus 3 and bus 4, so there is a series element, and accordingly we say that this series element is given by Y34 ACABC. So, it is Y and then this, and there are shunt is connected, here also shunt connected matrices. So, these two are termed as Y34 shunt ABC. So it is Y34 shunt ABC. Please note these are all. So Y34 shunt ABC. So this is bus 3, bus 4, bus 1, bus 2. So similarly, bus 1 and bus 2, so it would be Y12 AC ABC. Please note all these matrices are complex, so no big deal. And this is Y12 shunt ABC complex matrix. Similarly, here also Y12 shunt ABC. So these are, and in between there is a transformer model. That transformer model is given by Y1, Y2, Y3, Y4. Right. So this we have already seen that how to derive this, and in fact we have seen that depending upon the transformer primary connection mode, primary means that the transformer connection mode, that is whether it is connected in YY fashion, or whether it is connected to Y delta fashion, or whether it is connected to delta Y fashion, or whether it is connected to delta delta fashion. So then for same vector group, the even if the connections are basically different, but any transformer having these connections, either let us say YY or YD or DY or DD, they can be modeled as by this 6 cross 6 matrix. So please note all these are 3 cross 3 matrix, but this one is a 6 cross 6 matrix. And we know that this current and this current and this voltage and this voltage, they are related to this, right. So if I say that this is I2 transformer ABC, this is the current here, and if I see that this current is I3T transformer ABC, then I know that V2 ABC. So then I know that I2 T ABC, I3 T ABC, কোথায় গেল, Y2 Y3 is equal to Y1 Y2 Y3 Y4 and then we know that we have already proved it, V2 ABC and V3 ABC. So basically these currents which are entering into the transformer, they are related to the voltages by this equation, and we note that Y1, Y2, y3, y4 are all 3 cross 3 matrices. And we also know, and also for the connections as well as the vector group we have considered, also we have seen that y2 is equal to y3t. Although this relation will not use usually use much, but still we need to remember this, and we know how to calculate these four matrices y1, y2, y3, y4 for any given transformer connection such that yx, say let's say yg, ygx, yg, yx we have considered. Then with this we also know how to do ygx. Because we know this, so then I can basically consider yg dx, yg d sum x, then of course y dx, and then of course dy gx. Usually we have not done for dyx. Okay, and then if I know how to do y dx, we also know how to do dyx, and then lastly we have seen how to do d dx. Please note x is a vector group. Y is the star connection, and then delta D stands for the delta connection, and x we have already seen, and we also have seen that this x value would be 1, 3, 5, 7, 9, that is essentially the odd numbers if the two sides are of different type of connection, that is if let's say one side is y and let's say another side is d, then in that case the values of x would be odd numbers 1, 3, 5, 5, 7, 9, 11. On the other hand, if both these sides are same, for example either ygg or let's say ygy, that is if both these sides are same, that is both these sides are star, irrespective of the case that whether those star connections are grounded or not, that is if those both sides are let's say a star connected winding, so then in that case x would be an even number. And again similarly, if both these sides are let's say delta connected winding, then also the value of x would be another even number, and those numbers would be 2, 4, 6, 8, 10, 12. Of course this value of 12 is equal to again 0, because x means that this angular difference is x into 30 degree. So all these things we have seen. So now with this network we will start developing the network equations from the next lecture. Thank you.